The first thing you do when you see a limit is take the value that is underneath the limit. In this case, x goes to 3. Substitute in and see what happens. What happens to y when x is equal to 3? And then we'll decide. Then we need to talk about what happens to x, to y when x gets close to 3. So when we substitute 3 in here, we get 0 over 12, which is 0. This is very confusing to students. Often they think this is undefined, but it's only undefined if 0 is in the denominator. So this basically says when x is 3, y is 0. When you have a situation where you substitute a number into a limit and you get a number out, then you have already found the limit. The limit is 0. But let's see what this looks like on the graph. So here's the graph of x squared minus 9 over 2x plus 6. And I made a little table of values here to show what happens when x gets closer and closer to 3. So when we see at 3, y equals 0. We see at 2.9 we have negative 0.05. At 2.99, negative 0.005. 2.99, this would be 0.0005. This would be negative 0.00005. So we're seeing more and more decimal places here. The number gets smaller and smaller, closer to 0. And if we look at going the other direction, 3.01 would be 0.005, and then 3.001 would be 0.0005. Looks like I did this one more than once. Okay, well anyway, 0.00005, etc. Now if we zoom in on this graph here, okay, here's the situation. Here's the 2.9. When x is 2.9, y is 0.05. When x is 2.99, then notice y here, this is the x-axis where y equals 0. Notice now our y value is very, very close to the x-axis, so y is getting closer to 0. Here's where we have 2.99 getting closer and closer to 5. Here's our 3.01, 3.001. So notice we're getting really, really close to 0, and then we get right on the point. There's another one that's getting even closer to 0. I can zoom in on this even more, and you can see here's the 2 points where we're really, really close to 0 on either side, but when we're at 3, we're at 0. So we're saying the limit as x goes to 3 is 0. In other words, the closer I get x to 3, the closer y gets to 0. Now with a limit, it doesn't actually ever have to equal 0, it just has to get closer and closer. But in this case, it actually equals 0 when we get to 3. So this is a situation where we substitute a number in for x and we get a specific number for y. Now I could do the same thing with any other number. If I put in 1 here, I would get negative 8 in the numerator and positive 8 in the denominator. So at 1, let me actually do this over here. So if I did the limit as x goes to 1, I would of x squared minus 9 over 2x plus 6. Forgive me, I'm writing with my finger. It's not very easy here. 1 squared minus 9 over 2 times 1 plus 6. This would give me negative 8 over positive 8, which would be negative 1. So this tells me, this is saying as when x is 1, y is negative 1. So if I look at my graph here, so let me zoom back out. Wow, we had zoomed in a lot. Notice when x is 1, y is negative 1. Now if I got something really, really close to, and let me zoom in on this a little bit. So if I pick a point really close to positive 1 in the x direction, and notice that y is getting closer and closer to negative 1 when x is getting closer and closer to 1. And then we're right at 1. Notice over here on the other direction, if I make x closer and closer to 1, y is getting closer and closer to negative 1. So this is the definition of a limit. So anytime you have an actual point on the graph, the limit for a particular x-coordinate is just the y-coordinate if there's a point on the graph. So this is just a situation where there was a point on the graph at 3, 0, and 0 was the limit. Okay, let's look at the next example. The next example, if we if we go back and actually calculate the limit, okay, so I'm going to just go back and do a little creative erasing here. This becomes a minus. Okay, so this is minus 6, minus 6. We end up 0 over 0, which is undefined. Okay, so we have something that's undefined. Now we need to look and see what happens on the graph when we get this 0 over 0 situation. So I'm going to check, since there is no actual value, I'm going to just check and see what happens when x gets really, really close to 3 on this graph. So here we are. Here's where x is 3. And I've got some different values here. So I have here when x is 2.9, y is 2.95. When x is 2.99, y is 2.995. Here, when x is 2.999, y is 2.9995. I don't know if I can get one more in there. Now there's another one even closer. Similarly, if I'm on the other side, notice that as x gets really, really close to 3, y is getting really, really close to 3 as well. So there appears to be a limit here. By the definition of a limit, if bringing x closer to a certain number brings y closer to a certain number, then the limit exists. It's wherever y. Now if we actually click, oh, there's just one really, really close. Okay, we'll zoom in a little bit more. Now, here's 2 more where we're even closer. Now these are actually rounding, but if I click right here, see if I can kind of take a point. Okay, if I hit right here, notice that kind of an open circle, it sort of turns from a closed circle into an open circle. Notice right at 3, there is no y value. It's undefined. But there's no vertical asymptote or big gash. It's just a little bitty hole in the graph. It's saying I can get really, 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 really close to 3 in the x direction, and y gets really, really close to 3 as well, but I can't make x equal 3 because then y is undefined. But the limit still exists because the limit says getting x really, really close to 3 makes y really, really close to 3. So the limit is 3. Now how do you do that algebraically? Well, when we see this 0 over 0, we know that, okay, a limit does exist as long as these are both polynomial functions, which are the only ones we're working with right now. And we see this 0 over 0, we know we can cancel out a common factor, and find the limit. So I see putting x into both the numerator and the denominator gives me 0. That means x minus 3 has to be a factor of both the numerator and the denominator. So if I take this down here and rewrite my limit, factoring the numerator and the denominator, this factors to x minus 3, x plus 3, and the denominator factors to 2 times x minus 3. I can cancel out the common factor and then substitute 3 back in. So I get 3 plus 3 all over 2, which is 6 over 2, which is 3. So this tells me that the limit does equal 3. 3, 3 is the hole in the graph. Okay, so let's look at our third situation now. So turn this one off, and turn my third graph on. I'm going to zoom back out to see this graph here. Oh, maybe I never actually turned it on. Oh, I think I did turn it on. Ah, there we go. There's the graph. Okay, so here's where x is 3. Let's see what's happening on our little chart here. Okay, as x gets closer and closer to 3. Well, when x is 2.9, y is negative 25. When x is 2.99, y is negative 250. When x is 2.999, y is negative 2,500. When x is 2.9999, y is negative 25,000. The same thing happens on the positive end when x is coming from getting close to 3 but on the positive direction. So notice here, I'm moving towards 3 in the x direction. And what's happening to y? It's just getting bigger and bigger and bigger. Here I'm moving towards 3 from the numbers less than 3. What's happening to y? It's just getting bigger and bigger in the negative direction. When that kind of thing happens, that tells me I've got a vertical asymptote here. If we were to zoom out, we could actually see where some of those points are. Okay, it's kind of hard to see here, but okay, so here's my point. 299. Okay, so getting closer to 3 in the x direction does not make y get closer to anything. It makes y get farther away from any particular number. It just gets bigger and bigger and bigger in both the positive and negative direction. So this indicates a vertical asymptote. Now, how do you tell that from doing the limit? Okay, so this is 5 over 2x minus 6. So what does that look like when we actually calculate the limit? The limit as x goes to 3 of 5 over 2x minus 6. We get 5 over 2 times 3 minus 6. That's 5 over 0, which is an undefined number. But unlike the other undefined number we got 0 over 0, there is no common factor in the numerator and the denominator. There is a factor of x minus 3 in the denominator, but not another factor of x minus 3 in the denominator. So I cannot get rid of this discontinuity. This is what's called an infinite discontinuity. You can't find a limit for this one. Okay, so those are the three situations that can happen when you substitute a particular number into a function and try to find the limit. Either this right here, I'll kind of circle this one. Either you substitute a particular number in and you get a particular number out, and then you found your limit. That includes, remember our first example was 0 over 12, which is 0. That includes when you get 0, okay? That's just the number you get out. Or you put in a number for x and you get 0 over 0, which is undefined but fixable. We can cancel out a common factor, take the limit again, and find the limit. That limit is just the location of a hole in the graph. And the third situation is where you get a non-zero number over 0. That's when the limit is unfixable. The discontinuity is not fixable. There is no one number that y gets closer to as x gets closer to 3. It just goes off to infinity in both directions. You can see it's coming along here, hits 3, and just goes off to infinity in both directions. So those are the three situations. As x goes to a particular number, that's what can happen. Okay, I'll do the next case. In the next video, we'll look at what happens then as x goes to infinity.